let's do an example to find the Fourier expansion coefficients for a 25% duty cycle pulse train. So here we've plotted it out from LT Spice. It goes from 0 to 1 and it stays on for 0.25 seconds, and the period is 1 second. So T is 1 second. Now this is the equation to find the DC component, and we're just taking the average, right? We integrate over one period and divide by the period. That's the average, right? And here we can just see that what is the area here? It's just 1 times 0.25, right? So the area is 1 times 0.25, right? And so then the average is the area divided by the period, which is 0.25. And right, that's, I picked a period of 1 second, so that would work out. So if we go over to LT Spice and plot this out, right, if I control left click on VA naught, I get 250 millivolts. So that works. So now what I've done is multiplied the first harmonic, so the frequency is 1 hertz, times 2 times the cosine times the original function, and we get this shape. If we go back to LT Spice, what it is, here's the pulse, which then gets multiplied by the first harmonic, and so we get that value. All right, so I've just put this over here. Now again, this is the original function. We're multiplying by the first harmonic, right? And we're going to find the average, except we're multiplying it by 2. Now, you could do this several ways. You could find an area of a triangle, right? Which, right, would be 1/2 base times the height, which would be 1/2 times 0.25 times 1, right? You could also try to put a rectangle here, all right? Oops. And what I'm trying to do is in the first one, the triangle's area is smaller than the shape, so there's this error here, right? Now with by just putting a rectangle, right, I'm trying to average out whatever error over underestimated. So between here and here, so I mean, here's the original shape, right? And if I draw out here, right, I'm overestimating the shape here, but I'm also kind of underestimating it. And so I'm trying to get this area here and this area here to kind of match by eye, right? So that's 0.25 times 1.2, which becomes 0.3, and 0.25 divided by 2 this wasn't 1, it was actually 2. Excuse me. So 0.25 divided by 2 times 2 gives me a coefficient of 0.25 for the triangle and 0.3 for kind of doing a rectangle. All right. Now these are just estimates. You can tell that it's not 0, right? And it's positive, so that there is a cosine at the first harmonic that's existing. So we come back here and we just control left click on A1 and we get 318 millivolts, which yeah, I kind of knew the answer, so I knew to, rather than split it at 1, to come up a little bit higher, right? So you could think that I possibly cheated a bit. All right, so now let's find A2. So now we multiply the function times the second harmonic, right? And just for looking at it, and it will be easier if we draw a line through it, is that this area is going to be canceled by this area, and so the average area will be 0, right? So just kind of by inspection, A2 is 0. And left click on that. And, 325 nanovolts is effectively 0. So here, again, I can do the triangle method, or I can draw a box. This way it's a little easier to see, right? And I'm trying to get like this area and that area kind of in my mind to be about equal, right? But really that'll be, the rectangle will be 0.25 wide times 1.2 will equal 0.3. If I did it the triangle way, right, I would get 1/2. The base is 0.25. The height is 2. Okay, so we get the same answer as before. We can go and find that, and you'll see that it's 0.318. But on an exam or things like that, you can just do this kind of estimate, because we're trying to make sure that you understand that what does this mean, right? And by plotting it out and finding the area and dividing by the period, that's really what that equation says. All right, and then we'll go here, and now there's, again, 2 ways to do it. I can come here right, and I have a triangle that is now 0.125 times 2 right, but then you can see that there's 2 of them, so the whole thing would be by 2. And again, I could also do the rectangle method, where I'm just trying to fit the error, make the errors equal, right? And we're going to get 0.3 again. So .318. Okay. So what is the Fourier, the first few terms of a 25% duty cycle square wave? Now, there's actually an infinite number of terms, right? But we're just doing the first few. So xt will equal 0.25, right? Because that's a naught, plus 0.3 cosine 2 pi t. Now, plus 0 cosine 2 pi 2 times t. Right? Remember, a2 equaled 0. Right? Plus b1, which was 0.3 sine 2 pi t, plus 0.3 sine 2 pi second harmonic, right? And then these would go outwards. So that's pretty much it. In this particular series, right, it goes to an infinite amount. But if you were to look at the homework, maybe I take it up to number 3, right? If you wanted to see what were the harmonics at 3, right, you could come back and we call that A3, and then we have to multiply by the third harmonic, right? If we want B3, we multiply by the third harmonic. Okay, we run those, and let's do B3 first. So just looking at it, right, if I just draw a line through here, I'll see that this shape is kind of symmetric, right? And that if this were allowed to continue, the positive area would be canceled out by the negative area. But in this case, right, I can break this up into a triangle, this up into a triangle, so that's 2 positive triangle areas, but then I subtract 1 triangle area, right? So I'll get a positive constant, but it'll be, the net will be 1 positive triangle. And for A3, right, we can see that if this had started earlier, the areas would cancel out. So I have a positive area, right, which I can estimate with a triangle, and then I have 2 negative areas. So I'll have net 1 negative triangle area. All right, and I'll just we'll go back here and just kind of show you what I mean. So, right, if I just draw a line, okay, that's 0, right? So this is a positive area. That's a negative, that's a negative. You can see that it'd be the same, right? So all I have to do is draw a triangle here, right? And so that would be 0.125 would be the base. The height would be 2. And that would be 1/2, right? And so, yeah, that would be about 0.125. But we have a net negative. So it would be here. Let's go back and see how close we were. Minus 106 millivolts. So that's pretty good. So that should get you through a lot of the homework. Take care.